Effect size, Wikipedia audio. In statistics, an effect size is a quantitative measure of the strength of a phenomenon. Examples of effect sizes are the correlation between two variables, the regression coefficient in a regression, the mean difference, or even the risk with which something happens, such as how many people survive after a heart attack for every one person that does not survive. For most types of effect size, a larger absolute value always indicates a stronger effect, with the main exception being if the effect size is an odds ratio. Effect sizes complement statistical hypothesis testing, and play an important role in power analyses, sample size planning, and in meta-analyses. They are the first item in the magic criteria for evaluating the strength of a statistical claim. Especially in meta-analysis, where the purpose is to combine multiple effect sizes, the standard error of the effect size is of critical importance. The SE of the effect size is used to weigh effect sizes when combining studies, so that large studies are considered more important than small studies in the analysis. The SE of the effect size is calculated differently for each type of effect size, but generally only requires knowing the study's sample size, or the number of observations in each group. Reporting effect sizes or estimates thereof. Estimate of effect is considered good practice when presenting empirical research findings in many fields. The reporting of effect sizes facilitates the interpretation of the substantive, as opposed to the statistical, significance of a research result. Effect sizes are particularly prominent in social science and in medical research. Relative and absolute measures of effect size convey different information, and can be used complementarily. A prominent task force in the psychology research community made the following recommendation. Always present effect sizes for primary outcomes. If the units of measurement are meaningful on a practical level, then we usually prefer an unstandardized measure to a standardized measure. Overview. The term effect size can refer to the value of a statistic calculated from a sample of data, the value of a parameter of a hypothetical statistical population, or to the equation that operationalizes how statistics or parameters lead to the effect size value. Conventions for distinguishing sample from population effect sizes follow standard statistical practices. One common approach is to use Greek letters like ρ to denote population parameters and Latin letters like r to denote the corresponding statistic. Alternatively, a hat can be placed over the population parameter to denote the statistic, e.g. with ρ being the estimate of the parameter, ρ. As in any statistical setting, effect sizes are estimated with sampling error, and may be biased unless the effect size estimator that is used is appropriate for the manner in which the data were sampled and the manner in which the measurements were made. An example of this is publication bias, which occurs when scientists only report results when the estimated effect sizes are large or are statistically significant. As a result, if many researchers carry out studies with low statistical power, the reported effect sizes will tend to be larger than the true effects, if any. Another example where effect sizes may be distorted is in a multiple trial experiment, where the effect size calculation is based on the averaged or aggregated response across the trials. The metrics of variables being studied do not have intrinsic meaning. Results from multiple studies are being combined, some or all of the studies use different scales, or, it is desired to convey the size of an effect relative to the variability in the population. Sample-based effect sizes are distinguished from test statistics used in hypothesis testing, in that they estimate the strength of, for example, an apparent relationship, rather than assigning a significance level reflecting whether the magnitude of the relationship observed could be due to chance. The effect size does not directly determine the significance level, or vice versa. Given a sufficiently large sample size, a non-null statistical comparison will always show a statistically significant results unless the population effect size is exactly zero. For example, a sample Pearson correlation coefficient of 0.01 is statistically significant if the sample size is 1000. Reporting only the significant p-value from this analysis could be misleading if a correlation of 0.01 is too small to be of interest in a particular application. The term effect size can refer to a standardized measure of effect, or to an unstandardized measure. Standardized effect size measures are typically used when, in meta-analyses, standardized effect sizes are used as a common measure that can be calculated for different studies and then combined into an overall summary. About 50 to 100 different measures of effect size are known. These effect sizes estimate the amount of the variance within an experiment that is explained or accounted for by the experiment's model. Mean height equals 1750 mm, standard deviation equals 89.93 mm, women, mean height equals 1612 mm, standard deviation equals 69.05 mm. Pearson's correlation, often denoted R and introduced by Carl Pearson, is widely used as an effect size when paired quantitative data are available, for instance if one were studying the relationship between birth weight and longevity. The correlation coefficient can also be used when the data are binary. Pearson's R can vary in magnitude from 1 to 1, with 1 indicating a perfect negative linear relation, 1 indicating a perfect positive linear relation, and 0 indicating no linear relation between two variables. Cohen gives the following guidelines for the social sciences. A related effect size is R2, the coefficient of determination, calculated as the square of the Pearson correlation R. In the case of paired data, this is a measure of the proportion of variance shared by the two variables, and varies from 0 to 1. For example, with an R of 0.21 the coefficient of determination is 0.0441, meaning that 4.4% of the variance of either variable is shared with the other variable. The R2 is always positive, so does not convey the direction of the correlation between the two variables. Copylefted effect size confidence interval R code with R web service for t-test, ANOVA, regression, and REMC, online calculator for computing different effect sizes like Cohen's D, R, Q, F, D from dependent t-tests and transformation of different measures of effect size. Population and sample effect sizes. Eta squared describes the ratio of variance explained in the dependent variable by a predictor while controlling for other predictors, making it analogous to the R2. Eta squared is a biased estimator of the variance explained by the model in the population. This estimate shares the weakness with R2 that each additional variable will automatically increase the value of eta2. In addition, it measures the variance explained of the sample, not the population, meaning that it will always overestimate the effect size, although the bias grows smaller as the sample grows larger. A less biased estimator of the variance explained in the population is omega-2. This form of the formula is limited to between subjects analysis with equal sample sizes in all cells. Since it is less biased, omega-2 is preferable to eta2, however, it can be more inconvenient to calculate for complex analyses. A generalized form of the estimator has been published for between subjects and within subjects analysis, repeated measure, mixed design, and randomized block design experiments. In addition, methods to calculate partial omega-2 for individual factors and combined factors in designs with up to 3 independent variables have been published. Cohen's 2 is one of several effect size measures to use in the context of an F-test for ANOVA or multiple regression. Its amount of bias depends on the bias of its underlying measurement of variance explained. The 2 effect size measure for multiple regression is defined as. Likewise, 2 can be defined as the F2 effect size measure for sequential multiple regression, and also common for PLS modeling, is defined as relationship to test statistics. Standardized and unstandardized effect sizes. Cohen's F can also be found for factorial analysis of variance working backwards using compute.es, compute effect sizes, BES, one of RS packages providing confidence intervals of effect sizes based non-central parameters, Mix 2.0 software for professional meta-analysis in Excel. Many effect sizes available. Effect size calculators calculate D and R from a variety of statistics. Free effect size generator PC and Mac software, G*Power 3 power analyses and effect size calculation. Free software PC and Mac software, Power Up. Provides convenient Excel-based functions to determine minimum detectable effect size and minimum required sample size for various experimental and quasi-experimental designs. ESCalc, a free add-on for effect size calculation in Vista, the visual statistics system. Computes Cohen's D, Glass Delta, Hedges G, CLES, nonparametric Cliffs Delta, D to R conversion, etc., the ORDM package. Computes Cliffs Delta with a visual description of the results. Types. Correlation family, effect sizes based on variance explained. Pearson R or correlation coefficient. Coefficient of determination. Eta squared. In a balanced design of ANOVA, the corresponding population parameter of F2 is effect size. effectsizeeffect.com, measuring effect size, computing and interpreting effect size measures with Vista. Wherein μj denotes the population mean within the JTH group of the total K groups, and sigma the equivalent population standard deviations within each groups. SS is the sum of squares in ANOVA. Another measure that is used with correlation differences is Cohen's Q. This is the difference between two Fisher-transformed Pearson regression coefficients. In symbols this is omega squared, where R1 and R2 are the regressions being compared. The expected value of Q is 0 and its variance is, where N1 and N2 are the number of data points in the first and second regression respectively. A effect size theta based on means usually considers the standardized mean difference between two populations, 78. Where μ1 is the mean for one population, μ2 is the mean for the other population, and sigma is a standard deviation based on either or both populations. In the practical setting, the population values are typically not known and must be estimated from sample statistics. The several versions of effect sizes based on means differ with respect to which statistics are used. This form for the effect size resembles the computation for a t-test statistic, with the critical difference that the t-test statistic includes a factor of n. This means that for a given effect size, the significance level increases with the sample size. Unlike the t-test statistic, the effect size aims to estimate a population parameter and is not affected by the sample size. Cohen's d is defined as the difference between two means divided by a standard deviation for the data, i.e. Cohen's 2. Jacob Cohen defined S, the pooled standard deviation, as 67, where the variance for one of the groups is defined as Cohen's Q, and similar for the other group. The table below contains descriptors for magnitudes of d equals 0.01 to 2.0, as initially suggested by Cohen and expanded by Sokolowski. Difference family, effect sizes based on differences between means. Cohen's d. Glass delta. Other authors choose a slightly different computation of the standard deviation when referring to Cohen's d, where the denominator is without 2, 14. This definition of Cohen's d is termed the maximum likelihood estimator by Hedges and Olkin, and it is related to Hedges' g by a scaling factor. So, in the example above of visiting England and observing men's and women's heights, the data are: the effect size would equal 1.756 is found because the root mean square of the variances was used rather than the S as calculated above. This is very large and you should have no problem in detecting that there is a consistent height difference, on average, between men and women in the UK. With two paired samples, we look at the distribution of the difference scores. In that case, S is the standard deviation of this distribution of difference scores. This creates the following relationship between the t-statistic to test for a difference in the means of the two groups and Cohen's d. And Cohen's d is frequently used in estimating sample sizes for statistical testing. A lower Cohen's d indicates the necessity of larger sample sizes, and vice versa, as can subsequently be determined together with the additional parameters of desired significance level and statistical power. In 1976, Jean V. Glass proposed an estimator of the effect size that uses only the standard deviation of the second group, 78. The second group may be regarded as a control group, and Glass argued that if several treatments were compared to the control group, it would be better to use just the standard deviation computed from the control group, so that effect sizes would not differ under equal means and different variances. Under a correct assumption of equal population variances, a pooled estimate for sigma is more precise. Hedges G, suggested by Larry Hedges in 1981, is like the other measures based on a standardized difference, 79, where the pooled standard deviation, S, is computed as. However, as an estimator for the population effect size theta, it is biased. Nevertheless, this bias can be approximately corrected through multiplication by a factor. Hedges and Olkin refer to this less biased estimator, G, as D, but it is not the same as Cohen's d. The exact form for the correction factor J involves the gamma function, 104. A similar effect size estimator for multiple comparisons is the psi root mean square standardized effect. This essentially presents the omnibus difference of the entire model adjusted by the root mean square, analogous to D or G. The simplest formula for psi, suitable for one-way ANOVA, is. In addition, a generalization for multifactorial designs has been provided. Provided that the data is Gaussian distributed, a scaled Hedges G, n, 1, n, 2/ n, 1, plus, n, 2, g, n/\g, follows a non-central T distribution with the non-centrality parameter, n, 1, n, 2/ n, 1, plus, n, 2, theta, n/\theta, and degrees of freedom. Likewise, the scaled glass delta is distributed with n to 1 degrees of freedom. From the distribution it is possible to compute the expectation and variance of the effect sizes. In some cases large sample approximations for the variance are used. One suggestion for the variance of Hedges' unbiased estimator is 86. Mahalanobis distance is a multivariate generalization of Cohen's d, which takes into account the relationships between the variables equals chi 2 n c equals chi 2 n k 1 equals. Commonly used measures of association for the chi-squared test are the phi coefficient and Kramer SV. Phi is related to the point biserial correlation coefficient and Cohen's d and estimates the extent of the relationship between two variables. Kramer's V may be used with variables having more than two levels. Phi can be computed by finding the square root of the chi-squared statistic divided by the sample size. Similarly, Kramer's V is computed by taking the square root of the chi-squared statistic divided by the sample size and the length of the minimum dimension. Phi c is the intercorrelation of the two discrete variables and may be computed for any value of r or c. However, as chi-squared values tend to increase with the number of cells, the greater the difference between r and c, the more likely V will tend to 1 without strong evidence of a meaningful correlation. Kramer's V may also be applied to goodness of fit chi-squared models. In this case it functions as a measure of tendency towards a single outcome. In such a case one must use R for k, in order to preserve the 0 to 1 range of V. Otherwise, using C would reduce the equation to that for phi. Another measure of effect size used for chi-square tests is Cohen's W. This is defined as where P0i is the value of the ith cell under H0 and P1i is the value of the ith cell under H1. The odds ratio is another useful effect size. It is appropriate when the research question focuses on the degree of association between two binary variables. For example, consider a study of spelling ability. In a control group, 2 students pass the class for every one who fails, so the odds of passing are 2 to 1. In the treatment group, 6 students pass for every one who fails, so the odds of passing are 6 to 1. The effect size can be computed by noting that the odds of passing in the treatment group are 3 times higher than in the control group. Therefore, the odds ratio is 3. Odds ratio statistics are on a different scale than Cohen's d, so this 3 is not comparable to a Cohen's d of 3. The relative risk, also called risk ratio, is simply the risk of an event relative to some independent variable. This measure of effect size differs from the odds ratio in that it compares probabilities instead of odds, but asymptotically approaches the latter for small probabilities. Using the example above, the probabilities for those in the control group and treatment group passing is 2/3 and 6/7, respectively. The effect size can be computed the same as above, but using the probabilities instead. Therefore, the relative risk is 1.28. Since rather large probabilities of passing were used, there is a large difference between relative risk and odds ratio. Had failure been used as the event, the difference between the two measures of effect size would not be so great. While both measures are useful, they have different statistical uses. In medical research, the odds ratio is commonly used for case control studies, as odds, but not probabilities, are usually estimated. Relative risk is commonly used in randomized controlled trials and cohort studies, but relative risk contributes to overestimations of the effectiveness of interventions. The risk difference, sometimes called absolute risk reduction, is simply the difference in risk of an event between two groups. It is a useful measure in experimental research, since RD tells you the extent to which an experimental intervention changes the probability of an event or outcome. Using the example above, the probabilities for those in the control group and treatment group passing is 2/3 and 6/7, respectively, and so the RD effect size is 0.86. 0.67 equals 0.19. RD is the superior measure for assessing effectiveness of interventions. One measure used in power analysis when comparing two independent proportions is Cohen's H. This is defined as follows. H equals 2 arcsin P 1 arcsin P 2. Where P1 and P2 are the proportions of the two samples being compared and arcsin is the arcsign transformation. To more easily describe the meaning of an effect size, to people outside statistics, the common language effect size, as the name implies, was designed to communicate it in plain English. It is used to describe a difference between two groups and was proposed, as well as named, by Kenneth McGraw and S. P. Wong in 1992. They used the following example: in any random pairing of young adult males and females, the probability of the male being taller than the female is 0.92, or in simpler terms yet, in 92 out of 100 blind dates among young adults, the male will be taller than the female, when describing the population value of the common language effect size. The population value, for the common language effect size, is often reported like this, in terms of pairs randomly chosen from the population. Kirby notes that a pair, defined as a score in one group paired with a score in another group, is a core concept of the common language effect size. Hedges G. As another example, consider a scientific study with 10 people in the treatment group and 10 people in a control group. If everyone in the treatment group is compared to everyone in the control group, then there are 100 pairs. At the end of the study, the outcome is rated into a score, for each individual, and then all the scores are compared between the pairs. The results, as the percent of pairs that support the hypothesis, is the common language effect size. In the example study it could be 0.80, if 80 out of the 100 comparison pairs shows a better outcome for the treatment group than the control group, and the report may read as follows: when a patient in the treatment group was compared to a patient in the control group, in 80 of 100 pairs the treated patient showed a better treatment outcome. The sample value, in for example a study like this, is an unbiased estimator of the population value. Varga and Delaney generalized the common language effect size to cover ordinal level data. An effect size related to the common language effect size is the rank biserial correlation. This measure was introduced by Cureton as an effect size for the Mann-Whitney U test. That is, there are two groups, and scores for the groups have been converted to ranks. The Kirby simple difference formula computes the rank biserial correlation from the common language effect size. Letting F be the proportion of pairs favorable to the hypothesis, and letting U be the proportion of pairs not favorable, the rank biserial R is the simple difference between the two proportions, R equals FU. In other words, the correlation is the difference between the common language effect size and its complement. For example, if the common language effect size is 60%, then the rank biserial R equals 60% minus 40%, or R equals 0.20. The Kirby formula is directional, with positive values indicating that the results support the hypothesis. A non-directional formula for the rank biserial correlation was provided by Wendt, such that the correlation is always positive. The advantage of the Wendt formula is that it can be computed with information that is readily available in published papers. The formula uses only the test value of U from the Mann-Whitney U test, and the sample sizes of the two groups, R equals 1/. Note that U is defined here according to the classic definition as the smaller of the two U values which can be computed from the data. This ensures that 2U n1 n2, as n1 n2 is the maximum value of the U statistics. An example can illustrate the use of the two formulas. Consider a health study of 20 older adults, with 10 in the treatment group and 10 in the control group. Hence, there are 10 times 10 or 100 pairs. The health program uses diet, exercise, and supplements to improve memory, and memory is measured by a standardized test. A Mann-Whitney U test shows that the adult in the treatment group had the better memory in 70 of the 100 pairs, and the poorer memory in 30 pairs. The Mann-Whitney U is the smaller of 70 and 30, so U equals 30. The correlation between memory and treatment performance by the Kirby simple difference formula is R equals 0.40. The correlation by the Wendt formula is R equals 1/equals 0.40. Psi, root mean square standardized effect. Cliff's delta or D, originally developed by Norman Cliff for use with ordinal data, is a measure of how often the values in one distribution are larger than the values in a second distribution. Crucially, it does not require any assumptions about the shape or spread of the two distributions. The sample estimate, D, is given by distribution of effect sizes based on means. Where the two distributions are of size, n, and m, with items, x, I, and x, j, respectively, and is the Iverson bracket, which is 1 when the contents are true and 0 when false. D, is linearly related to the Mann-Whitney U statistic, however it captures the direction of the difference in its sign. Given the Mann-Whitney, U, D, is. Other metrics. Categorical family, effect sizes for associations among categorical variables. Confidence intervals of standardized effect sizes, especially Cohen's, D, and F, 2, rely on the calculation of confidence intervals of non-centrality parameters. A common approach to construct the confidence interval of NCP is to find the critical NCP values to fit the observed statistic to Tail-Schwann tiles alpha/2 end. The SAS and R package MBES provides functions to find critical values of NCP. For a single group, M denotes the sample mean, mu the population mean, SD the sample's standard deviation, sigma the population's standard deviation, and n is the sample size of the group. The t-value is used to test the hypothesis on the difference between the mean and a baseline mu baseline. Usually, mu baseline is 0. In the case of two related groups, the single group is constructed by the differences in pair of samples, while SD and sigma denote the samples and population's standard deviations of differences rather than within original two groups. And Cohen's W. Odds ratio. Relative risk. Risk difference. Cohen's H. Common language effects size. Rank biserial correlation. Effect size for ordinal data. Confidence intervals by means of non-centrality parameters. T-test for mean difference of single group or two related groups. T-test for mean difference between two independent groups. One-way ANOVA test for mean difference across multiple independent groups. Effect sizes descriptors. Is the point estimate of so N1 or N2 are the respective sample sizes, wherein N Cohen's so one-way ANOVA test applies non-central F distribution, while with a given population standard deviation, sigma, the same test question applies non-central chi-squared distribution. For each JTH sample within ITH group Xi, J, denote while so, both NCP of F and chi 2 equate. In case of n equals n 1 equals n 2 equals n k equals n equals backslash k dots equals n, for k independent groups of same size, the total sample size is n equals nk. The t-test for a pair of independent groups is a special case of one-way ANOVA. Note that the non-centrality parameter, n, c, p, f, of f is not comparable to the non-centrality parameter, n, c, p, t, of the corresponding t. Actually, n, c, p, f, equals n, c, p, t, 2, equals ncp, and f, equals d, 2, equals backslash left backslash right. Whether an effect size should be interpreted small, medium, or large depends on its substantive context and its operational definition. Cohen's conventional criteria small, medium, or big are near ubiquitous across many fields, although Cohen cautioned. The terms small, medium, and large are relative, not only to each other, but to the area of behavioral science or even more particularly to the specific content and research method being employed in any given investigation. In the face of this relativity, there is a certain risk inherent in offering conventional operational definitions for these terms for use in power analysis in as diverse a field of inquiry as behavioral science. This risk is nevertheless accepted in the belief that more is to be gained than lost by supplying a common conventional frame of reference which is recommended for use only when no better basis for estimating the ES index is available. In the two-sample layout, Sokolowski concluded based on current research findings in the applied literature, it seems appropriate to revise the rules of thumb for effect sizes, keeping in mind Cohen's cautions, and expanded the descriptions to include very small, very large, and huge. The same de facto standards could be developed for other layouts. Length noted for a medium effect size, you'll choose the same N regardless of the accuracy or reliability of your instrument, or the narrowness or diversity of your subjects. Clearly, important considerations are being ignored here. Researchers should interpret the substantive significance of their results by grounding them in a meaningful context or by quantifying their contribution to knowledge, and Cohen's effect size descriptions can be helpful as a starting point. Similarly, a U.S. Department of Education-sponsored report said the widespread indiscriminate use of Cohen's generic small, medium, and large effect size values to characterize effect sizes in domains to which his normative values do not apply is thus likewise inappropriate and misleading. They suggested that appropriate norms are those based on distributions of effect sizes for comparable outcome measures from comparable interventions targeted on comparable samples. Thus, if a study in a field where most interventions are tiny yielded a small effect, these new criteria would call it large. In a related point, see Abelson's paradox and Sokolowski's paradox. Online applications. Software. Further explanations.